Hello everybody, thank you for joining my presentation. I am Benjamin Kellenberger and today I'm going to take you on a walk through a digital savanna. And this is joint work with Dirk van der Wijn from Wageningen University in the Netherlands and Davis Truya, also from EPFL in Sion, Switzerland. Title you might be able to guess what this is going to be about. But first, what we're going to do is we're going to detect some wildlife. And we're not going to detect wildlife like from the ground, from camera traps, like this elephant here. But what we're going to do is we're going to identify these mammals on land in drone images, like this one, taken in Kenya. You might be able to spot straight away that there is, for example, a giraffe in the middle of the screen here. Also, if you look a bit closer, you will see that there's some other flocks of large mammals and so on. The main problem is that the more you look, the more animals you find, which at first sounds exciting, but then the question arises on how easy it is to label all of these images for animals if you, for example, want to train an automated wildlife detector afterwards. Because in some cases, it might actually be very difficult to find these animals, like this group here in the top, which is cut off by half of the image. And in some other cases, you have effects like shadows and big trees, which makes it nearly impossible to identify all of the animals. Here, for example, you have to zoom in really closely in order to find that this actually contains 4 of the largest land-going mammals currently alive, elephants. So you can see that labeling these images by hand can be very frustrating and very difficult to do. So what we're going to do instead here is to use synthetic data, coming from example from a computer rendering engine, like here on the screen, which shows the Cynthia dataset. This image represents it fairly well that synthetic data has been used in the computer vision scene for quite a while, especially for tasks which are not only tedious to label, but where it is difficult to obtain accurate data for training, like for self-driving cars, where you cannot collect data from real accidents. And in our case, we want in principle to just relieve annotators from having to label so many images. And what we're going to do is we're going to use AirSimW, which is a rendering environment on of an African savanna based on the AirSim package, which has been designed for synthesizing images for drones and is using the Epic Unreal Engine. And AirSimW, as I said, contains scenes from an African savanna. And here's a rendering from high above of it. And if you get a bit closer, you can see that it basically is a pretty nice African environment. Here, it seems to be dusk. You can see some crocodiles and some, I think, rhinos grazing there. You can see some hippos in the pond. So it contains animals, it contains trees and bushes. It also contains a few poachers and some vehicles to make it as hopefully realistic as possible. But of course, rather than just browsing around and viewing at some nice images, we want to use this environment to create training data for a subsequent object detector. And the way we do this is we first define a data acquisition schedule. So what we do is we take nadir images, so top down, looking perpendicularly to the ground, within 1 square kilometer around the center of the environment. So the environment is not so big, and we found that most of the animals are actually gathered around the center of it. So what we do is we take our virtual drone and fly it at 20 to 60 meters of height, and we start from the center of the environment and then select a random point within this 1 square kilometer and fly towards it in a diagonal way until we reach either the latitude or the longitude of this point, from which on we fly straight. And we take a picture at every 3 to 5 meters, depending on the height. And like that, this gives us quite a lot of data to play around with to train our model. And here's a little video of what this looks like in action. You can see the drone in the middle, and what we're basically doing here is we're repositioning it within 3 to 5 meter steps and taking a picture every time we do it. And on the bottom, you can see a view of the front-facing camera of the different products that AirSim can give us. So in the left, you can see a height map, which we get for free as well. In the middle, you can see a semantic segmentation map, which we will be using to detect our animals. And in the right, you can see the image that it takes. And as I said, this is the front-facing camera, but we are using the bottom face, the downward-facing camera. And so we did that and collected a couple of thousand images, and you can see the concentration of the images within the center as shown on the screen. This shows the latitudes, or the X and the Y axis within this virtual environment. Here's an example product of what this looks like. You can see the rendered image with some animals in the left and the semantic segmentation mask in the right. And here, naturally, we only keep the blue animal segmentation masks and we extract bounding boxes from it. Of course, the most straight away way of doing that is to draw boxes as per minimum bounding rectangle. But we ran into a little bit of a problem with that because sometimes animals touch each other. So at least the segmentation masks do. Like in the left case here, where the two bottom animals are combined into one. And in order to disentangle that, we apply some simple mathematical methodology by means of first eroding the segmentation masks, then assigning individual pixel IDs and dilating the mask again afterwards, so that we could make sure that all the animals are represented by one bounding box each. So much about the synthetic data. Now let's go to the real data, which comes from Namibia. You might have, if you have seen one of my previous presentations, you might now be familiar with this dataset. And there's a good reason for that. We wanted to use one where we know how well a model, and this happens to be the Kusikus, which is taken over the Kusikus Reserve in Namibia, which is a private wildlife park of about 110 square kilometers. And we've taken this data in 2014, and it has about 4 to 8 centimeter resolution, about 650 images, and contains a total of about 1,100 animals. And of course, we use this as a target in order to see how our model trained on AirSimW performs. But what we also do is we try intermediate models. We try mixtures of the two data sets. More in detail, our baseline is the AirSimW only model, which was trained on 5,000 of AirSim data. Then we have two models trained on a mixture of the two, of 5,000 AirSim and 1,000 Kusikus. The first model was trained with both datasets combined from the start. And in the second, we first train on AirSim and then fine-tune on Kusikus. And finally, we construct an upper bound scenario where we train on 8,000 of the Kusikus images, the real ones. For model, we use an off-the-shelf RetinaNet with 18 feature extractor, and we apply a little bit of data augmentation by means of random horizontal flips and a bit of Gaussian blurring to simulate realistic drone acquisition conditions. And finally, we also apply non-maximum suppression at test time in order to retain only the most meaningful around the animals. With that, let's dive straight into the results. With this, you can see the precision recall curves here, and this ranges from the AirSim only model in purple over the mixed model in blue and green to the Kusikus only, the exclusively real model in orange. Now, the first thing you can see is that all models get a relatively high recall of about 80%, but there is quite a big difference between the exclusively rendered and the mixed and the real ones. Now, of course, the real model in orange performs best, which is unsurprising because it has been trained on the most similar data, but it still is surprising that the rendered only model manages to find quite a lot of animals indeed. You can see its precision is low, but it finds 80% of the animals after all. And even more impressive is that if we take the mixed model, especially the fine-tuned one, where we first train on AirSim and then apply it on Kusikus, we get an almost as good accuracy as the exclusively real model, just a little bit of sacrifice in recall and precision. So basically, we were able to reduce the number of images that have to be labeled from 8,000 to just 1000, which is great. Visually, here's an example of what this looks like. On the left is the render model, and you can see it finds all the animals, but makes a lot of false positives, which is as we've seen. The fine-tuned model in the middle is not the best in recall, as we've seen, but it is much more precise. And unsurprisingly, the exclusively real model finds all the animals and does not commit too many false alarms, which is good. Now, at this point, I guess I have to address the elephant in the room, which you might have been asking yourself while watching this presentation. And that is, we have this rendered data and we have the realistic data. So what about domain adaptation? Why don't we, for example, use a GAN to make the rendered data look as realistic as possible? Well, of course we tried. And what we did is we tried a cycle GAN, which we found to be the most stable to train and to produce the best results. And just quickly, the way cycle GAN works is we have our two domains. On the top is the real cousicous data, and at the bottom is the real airsim renderings. And we apply a generator, in this case a unit, for example, which maps to the real cousicous to a fake representation in the airsim domain. And we do the same the other way around. And finally, because it is a cycle GAN, we have inverse generators which map these fake images back to the original domain, and then we minimize losses with discriminators and so on. These are not shown because the slide would become too convoluted otherwise. So if we apply a cycle GAN, we get results. The left is the input, a real airsim rendering with animals, and in the right is what it does in order to reflect the cousicous distribution. Now, color-wise, this is a pretty good match. You can see that the trees still kind of look like trees, and the animals are still there, which is great. There are a few artifacts, like in the bottom right, but other than that, this looks okay. So now let's have a look at what it does the other way around. So from cousicous to, the other way around, it doesn't really work. So the left is the cousicous input, and in the right is what the cycle GAN does out of it. On the top, you can see that the trees are still represented very well. But if you look at the animals in the bottom right, you can see that these have suddenly been converted to bushes, which is not what we want. This is not going to help the model in any way. So now you might be saying, well, let's just use the other GAN part, because from airsim to cousicous, it seems to work. Well, it doesn't. And here's the story. The problem is that this whole scenario is ill-posed, in that the model doesn't know what an animal is supposed to look like. So in natural images, this works, because in this case, the zebras and the horses cover the majority of the image portion. So the generator in the GAN automatically assigns its mass to the center object. In our case, however, this is not true. Animals are a pretty rare sight and they're very small. So all the model can do is to assign these artifacts the second most frequent class, which is bushes in this case. So naturally, all the animals turn into bushes. And we have tried many things. We've gone to literature and we tried different tricks in order to improve this GAN story, from different architectures to conditioning on the segmentation mask that we have, etc. And all of these failed so far. Basically, all the models we tried resulted in animals becoming weird artifacts and sometimes turning into bushes. So as a result, whenever we train it on these GAN transformed images from airsim, it would not work at all in the real cousicous domain. This is how far we've been able to go with this project, and hence this marks the end of the presentation. However, if you feel like you have a great idea of disentangling the animals and the trees, or would like to contribute, we would be very happy to share the data with you and to collaborate accordingly. But for now, I'm open for questions. Thank you very much.